So this is the first homework for the course. It's due 2015 September 13th, Sunday midnight by email. So if you are past the due date, then you'll, for each day you're late, you'll get 10% less. It's explained in the syllabus. So the evaluation for this course is homework 40%, and then the rest are exams. So the homeworks will include reading assignments, and then you'll have to discuss some of those assigned reading and some programming in Python, but this will not be from scratch. Most of the time it will be modifying my programs and problems. So it will also include homework, will also include problems from the textbook. And exams will not require calculators or computers. It will require deriving equations but not solving them. And if there are numerical errors, then as long as the process is explained properly, it will get full marks. So the homework is to read the following paper in full and make a list of any terms or concepts that you don't understand. And you don't need to worry if it's you don't understand a lot of things. Just make a list. And so this is the case most of the time in multidisciplinary study. So engineering people studying biology or math, or computer people studying mechanical engineering. So there will be a lot of things that you don't understand, but that means you can follow up by taking more time to understand it if you need to. So let me know by coming Sunday, September 6th, if you can't find this paper in the internet. So try using Google Scholar, and the paper, I'll give you a preview. Looks like this. So it's a conference paper from Japan, and they're trying to make robotic arms that can cooperate with humans. So if the robotic arm is very jerky, then it cannot cooperate too well with a human. So to model the robotic arm, or to model the human arm, they've used a spring mass-like model. So there's biceps and triceps in the upper arm, and they control the elbow joint. And this is modeled as a spring damper system. So instead of eta, they've used C. So this is not a common symbol for the damping coefficient. It means the same thing. So the homework is to read this paper, and it doesn't matter if you don't understand it in full. So you just have to read it and list the concepts or terms that you don't understand. And the second part of the homework is to try the following problem. That is the same problem that we derived in the last few sections, this equation, but I'm using values. Mass equals to 1 kg. This is like 1 kilogram is like a common item. For example, a liter of water could be 1 kilogram, and the spring constant 2000 newtons per meter, and the damping coefficient of 55 newtons second per meter. These I took from the paper. If you look at this paper, what you can see is that they tried to measure the spring constant of the human biceps or triceps, and the damping coefficient. And what you can see is that they measured a certain value, but it changed over time. So even the spring constant changed and the damping coefficient changed, but before it changed, it was stable at a certain value when it was not moving, and it was minus 2055. So I've used these values from there just as a starting point for just for the sake of the problem, and then I will demo this. I write the program in Python to uh, solve this problem. It's not very long, and then what you have to do is you have to try to reproduce what I did in your own computer, and um, then you have to change some of the parameters. For example, what happens if the damping is decreased by 10 times? What happens if damping is increased by 10 times? And you have to provide a printout of the program and the results. So if you do it as a notebook, then the results and the method are all in the same file, and you have to print it as a PDF or just the notebook and send it to me. And then you have to change the spring stiffness and repeat the result.